My name is Leila. I work at Shopify as a site reliability engineer. I'm part of the resiliency organization at Shopify, which has more than around 50 engineers whose job is to ensure that Shopify is ready and reliable for merchants and buyers across the globe. My talk today will be about a project where we improved the Elasticsearch indexing performance, as well as the reliability of our search infrastructure by using dedicated node pools that are automatically scaled by using KEDA scalers. In the next 30 minutes, we will learn how at Shopify we host the search infrastructure on top of Kubernetes. We will talk about the entire data pipeline that writes data from SQL to Elasticsearch through Kafka and the resilience of its architecture. I will follow by presenting the problem we needed to solve, and we'll share our solution for it, followed by some technical details on how to use KEDA for scaling workloads. And I will conclude the presentation with a Q&A. Shopify is the all-in-one commerce platform to start, run, and grow a business. It is the leading global commerce company that provides essential internet infrastructure for commerce, as well as trusted tools to start and scale a retail business of any size. Currently, we have over 3 million merchants and businesses using our platform. We have merchants like Gymshark and Fashion Nova selling their products with us, and we represent over 175 countries and have about the 10% of total US commerce. And in the summer of 2024, we reached $1 trillion in GMV, which stands in gross merchandise value. One of the largest events in commerce is the Black Friday Cyber Monday week, which we call it BFCM. To share more stats about the scale of Shopify, during the BFCM of 2023, around a year ago, Shopify processed 145 billion requests in a day, peaking around 60 million requests per minute, which led to a total of $4 billion in GMV. Search is a fundamental part of any commerce platform, allowing buyers to search and filter products, and also merchants to fulfill orders and manage their customers. When you go to any online store and search for products like sneakers, your request goes to a search engine that is backed by a secondary data store, which is different from traditional databases. And we call the secondary data store the search engine. The search engine that Shopify uses is Elasticsearch. So a quick refresher on what Elasticsearch is. Elasticsearch is a distributed text search and analytics engine, which is built on top of Lucene, that has full text search capabilities that are well suited to the e-commerce domain. It's also a scalable and fault-tolerant system, and it handles a lot of the hard parts of running a distributed system very well. Elasticsearch stores data that share similar characteristics in a logical namespace called an index. And these indices are split into multiple shards, which can be either primary shards or replica shards. We run our fleet of Elasticsearch clusters on managed Kubernetes clusters, GKE on top of GCP. And we deploy and maintain them using a custom Kubernetes controller that we have built. Shopify is a large and complex ecosystem, which is made up of a variety of apps and services. And the biggest service at Shopify is called the Shopify Core, which is a big Rails monolith that powers all of our merchant shops and storefronts. We run Shopify in GCP regions for resiliency. And what you're looking at here is a high-level structure of Shopify Core in a single region. So entire Shopify Core in a region is broken down into above 100 logical groups of SQL databases and instances of other services, which are simplified and not shown in this slide. All of these services power all of our online store functionalities for shops running in that region. And we run one instance of Elasticsearch for Shopify core that provides search functionality for the shops running in that region. To give more context, Elasticsearch is used as a secondary data store. It is utilized to provide additional functionalities such as, such as fast search capabilities, aggregations, or full text search, on top of the existing data that is stored in the primary data store. We have an ingest pipeline in each region that consists of Kafka topics and Kafka consumers. We produce updates made to records for all SQL instances in the region to our Kafka topics, and our consumers pick them up and pick those messages up from Kafka topics and write them to the right Elasticsearch index in real time. Indexing is a term we will use a lot in this talk. It is the act of writing documents from the primary data store to Elasticsearch. And we store the Elasticsearch documents in Elasticsearch indices. For example, we have an index that allows merchants to search and filter through the orders they have received, or another one that allows them to search through their store's products. Buyers or merchants search for the information stored in the Elasticsearch, and the queries are sent to the correct index shard through a routing layer. And our focus in this talk will be on the indexing path that is shown here, which we call it the indexing pipeline. In the previous slides, we saw the indexing pipeline that brought data from SQL as the primary data store to Elasticsearch through Kafka. But that was simplified, and we have actually built two different indexing pipelines for two different write profiles. Thank you so much. Thanks. One of the indexing pipelines is called the real-time pipeline, which, for example, indexes a product to Elasticsearch and makes it available for search for buyers when a merchant creates a new product in the online store. The other one is called the Reindex pipeline. We have a lot of developers at Shopify, and they create indices, modify index analyzers, and add or remove fields from them. And when that happens, we need to migrate all that data to a new version of the index, and later promote that index to make the new feature available to the merchants and buyers. We call this reindexing, which basically means building an entire Elasticsearch index and getting all the historical data from SQL to the new Elasticsearch index, and build it all over again. And as I just mentioned, we have two separate indexing pipelines for real-time and reindex writes, which we see on this slide. As a bit of a background, Kafka is a distributed publish-subscribe messaging system. Data is written to Kafka topics by producers and consumed from those topics by consumers. We have separate Kafka topics for each pipeline. The real-time Kafka consumers consume from the real-time Kafka topic and write to the production indices. These indices provide search results for buyers and merchants. The reindex consumers, on the other hand, they do not write to the production indices. They only write to indices whose aliases end with a .new. The .new indices, an example you see here, get created when we start a reindex for a specific index, for example, for the orders index. The orders.new index will eventually be a copy of the production index for orders, but with different mappings or fields. A new index does not receive production queries because its data is incomplete until all the necessary records from SQL has been written to it. After the .new index is created, some jobs get spawned and read the necessary records from SQL, produce them to the reindex Kafka topic, which will be consumed by the reindex consumers, and will be written to the .new index later. And to make sure that the new index also receives real-time updates and doesn't get stale, the reindex topic also receives real-time updates made to SQL. And well, after a while, all the historical records from SQL will get processed and no more reindex writes will be produced to the reindex Kafka topic. At this point, the reindex is finished and we can flip the new index live. Flipping it live basically means changing the alias for the production and new index. After this, the new index will become the production index and will have the updated mappings or fields and will be queried by the clients. As I mentioned before, our Elasticsearch clusters run on Kubernetes on top of GCP across different regions and availability zones. It's good to know that today the entire Shopify ecosystem, including the Shopify core and its storefront, run across the globe from North America to Europe and Singapore. We have Elasticsearch clusters spread across these regions, giving us resilience and availability through redundancy. This is SREcon, so let's talk more about resilience. Taking a closer look as an example GCP region where Shopify core and its Elasticsearch cluster runs, we have the indexing pipeline updating Elasticsearch when changes are made to SQL records. We can see here that search queries are sent to Elasticsearch through a routing layer, meaning that queries made to shops in a certain region are routed to the Elasticsearch in the same region. We know that the first step towards high availability is redundancy, and to mitigate regional failures, we should replicate our system to another region. The active SQL instances and Kafka topics in different regions hold different data sets, and we need to replicate their data between regions so both Elasticsearch clusters have the same data set. With this inter-region data replication, if one of the Elasticsearch clusters goes down, we can fail over the query traffic to the Elasticsearch cluster that is functional until the other one has recovered. At the application layer, Elasticsearch also provides fault tolerance by being zone aware, meaning that if we deploy our Kubernetes cluster across 3 availability zones, when Elasticsearch distributes primary and replica shards, it distributes them across these zones in a way that the primary and replica for one shard do not end up in the same availability zone. And a quick refresher on Kubernetes pods. They are the smallest deployable unit in Kubernetes and are designed to run containerized applications in a Kubernetes cluster. The application in this case is Elasticsearch. We use node affinity rules to ensure that 2 pods from the same Elasticsearch cluster do not end up on do not get scheduled on the same GKE node. And we also taint the GKE nodes, so only the Elasticsearch pods are deployed on them. And the Elasticsearch pods are given the right tolerations so they can be scheduled on the right GKE nodes. With this zone-aware settings, we can also do maintenance more quickly as we can bring down an entire availability zone for maintenance without being worried about data loss. To give a sense of the scale of search at Shopify, as of today, the search platform team manages above 100 distinct Elasticsearch clusters, some of which are as large as 260 node clusters. And together they store more than 3 petabytes of data. For Shopify core Elasticsearch, the real-time indexing rate can peak at 90,000 documents per second, while our reindex pipeline indexing rate peaks at around 500,000 documents per second. And as you can see, the reindex pipeline throughput is a lot higher than that of the real-time pipeline. And to recall, reindexes are done and run occasionally, and there are an occasional burst of writes to Elasticsearch. And actually, this is a nice segue to the problem statement, which will be followed by the solution. What you see in this slide is a distribution of Elasticsearch nodes or pods across many VMs running on GCP. As mentioned before, an Elasticsearch index is split into many shards, and each shard has a replica. And for example, the production index for orders is split to 1,024 primary shards, and each of them have a replica shard that is shown here by a different color. And this index receives real-time writes and as well as production queries. When a reindex starts for maintenance, another index called the orders.new is created on the same VMs, which will receive the heavy reindex writes. And since the production and the new index share the same compute and storage resources, the heavy reindex writes will impact the real-time writes and slow them down. And delayed real-time indexing results in stale or inaccurate search results, which could result in lost revenue for our merchants. So the fact that real-time and reindex writes share the same compute and storage resources leads to reindexes impacting production writes and queries, which leads to pager fatigue because the on-call would get paged for real-time indexing delay, which can only be mitigated by stopping the reindex. That also slows down feature rollouts for developers. And our initial approach to solve this problem at Shopify was to over-provision the cluster to always be ready to handle reindex load. This became too expensive as Shopify kept growing, and the cost was no longer acceptable. So we decided to separate the infrastructure for real-time and reindex writes. This was a huge undertaking because it required us to make some fundamental changes to our existing reindex pipeline. And the first step to do this was to create a separate GKE node pool just for running reindexes. And we leveraged Kubernetes taints and tolerations to ensure that Elasticsearch pods for reindexes only get scheduled on the reindex GKE node pool, same as for Elasticsearch pods for real-time writes. Just as a quick refresher, a Kubernetes taint is a mechanism that allows a node to repel a set of pods. And taints are applied to nodes, and they work together with tolerations, which are applied to pods. The primary purpose of using taints is to ensure that certain pods are not scheduled on the inappropriate nodes. So giving the reindex and real-time tolerations to pods will ensure they get scheduled on different node pools, which will provide the first step towards isolation of reindex and real-time writes. We use the Elasticsearch built-in shard allocation settings to force all indices to be hosted on the Elasticsearch pods that run on the real-time node pool, and except for the ones whose aliases end with a .new, which should be hosted on Elasticsearch pods that run on the reindex node pools. This is how we separated the .new indices from the production indices. Once the reindex is done, we switch the alias for the .new index, which will force that index's shards to be relocated to the real-time node pool and become searchable by clients. In this way, reindexes no longer impact production reads and writes. Also, since the real-time node pool no longer has to provide for the heavy reindex writes, there is no need to over-provision it, and it gives us a great opportunity to save infrastructure costs. But as you see here, now it is the reindex node pool that is burning money. And this is where node autoscaling will come in handy. Ideally, we would need a very small GKE node pool that gets scaled up only when the reindexes start. And we expect that the node pool scales up depending on the size of the index we want to backfill. For this purpose, we picked KEDA, which stands for Kubernetes Event-Driven Autoscaling, which is an open source project that provides autoscaling for Kubernetes workloads. It is designed to extend the capabilities of Kubernetes Horizontal Pod Autoscaler, the HPA, by allowing workloads to scale based on metrics from various event sources rather than just CPU or memory utilization. This makes KEDA particularly useful for applications that need to scale in response to events like the queue length, number of incoming messages, or in our case, to automatically scale up the Kubernetes workload when a reindex starts. Scaling up the workload will force the GKE node pool that is hosting the reindex pods to be expanded as well. KEDA is implemented as a Kubernetes operator, which uses custom resources to define how scaling should behave. It consists of two main components. One is the KEDA controller that watches for a KEDA custom resource called the scaled object and manages the life cycle of the corresponding HPA resources. The other one is the metrics adapter that collects and provides metrics to the Kubernetes HPA, which then makes decisions about scaling the application pods based on these metrics. KEDA supports a variety of event sources called the scalers, and Prometheus is one of them. Each event source is represented as a trigger in the KEDA configuration. Scaled objects are custom resources used for scaling deployments, stateful sets, or any other scalable Kubernetes workload. We define the triggers and scaling behavior used by KEDA to scale workloads. You see an example of a scaled object on the slide. For our specific use case, we set the scale target to our reindex stateful set that runs the Elasticsearch pods that are used for reindexes. We also have settings for min and max replica counts. These settings determine the minimum and maximum number of replicas that the stateful set can scale to based on the events that are triggering the scaling action. For us, we set the minimum as low as 3 and the maximum to around 200 replicas. The Prometheus trigger in KEDA enables autoscaling based on the result of a Prometheus query. When you configure a scaled object with a Prometheus trigger, KEDA will periodically send queries to a specified Prometheus server, and the responses to these queries are then used to make decisions about scaling the Kubernetes workload up or down. For our use case, we wrote a Prometheus query that calculates the number of shards divided by the number of nodes. We set the threshold to 1, which means that ideally for peak performance, we want to have 1 shard on a single node. However, if the index that we are reindexing has like 2,000 shards and the max replica count is set to 200, we will end up only with 200 nodes, which means we will have 10 shards per node. So there is a maximum. The following slides show an example for node autoscaling. We have a real-time node pool hosting shards for production indices. We also have a reindex node pool with a minimum of 3 nodes that initially host no indices because no reindex is running. Therefore, the Prometheus query for KEDA that calculates the number of shards divided by the number of nodes returns 0. KEDA compares the query result to the threshold we have set, and which is 1, and decides to do nothing because the node pool already has 3 replicas, which is the minimum allowed. If the minimum allowed was lower, KEDA would scale it down further. Next, the reindex starts for an index that has 4 primary shards and 4 replica shards, so 8 shards in total. Because of the routing allocations that we have set for Elasticsearch, the shards of the .new index will be created on the nodes of the reindex node pool. Once this happens, the Prometheus query will return a value higher than our threshold of 1, which signals to KEDA to scale the node pool up, actually to scale the reindex stateful set up, and until the result for the query becomes equal to the threshold. So we will have 8 VMs after this. Once the node pool gets scaled up, Elasticsearch automatically balances the shards across the nodes, so each node of the node pool will have 1 shard. Now the Prometheus query returns 1, which is equal to the threshold, and KEDA will take no scaling actions. After the reindex is done and we switch the .new index live, all shards from the reindex node pool get evacuated and will get scheduled on the real-time node pool. At this time, the Prometheus query returns 0, which is below the threshold, and consequently, KEDA decides to scale down the reindex node pool. The reindex node pool gets down to the minimum number of nodes, which is 3 in our case, and KEDA will take no further action until a new reindex is started. So to summarize, with dedicated reindex nodes, we were able to reindex our orders index, which is our largest one and has around 100 terabytes of data, 40% faster. The queued write threads on the real-time nodes was also dropped by 98% during reindexes, which helped improve real-time writes performance. As a result, the pager fatigue due to this problem was no longer an issue, and developers were able to ship features faster. And leveraging node autoscaling, we were able to reduce the total number of CPU cores and memory used by our real-time node pools by 58% and 15% respectively, which led to a total saving of 43% in infrastructure costs. This was only an example of the interesting problems we solve at Shopify. We're always looking for people who are interested in solving problems at scale. If you are interested, scan this QR code or come talk to me. We're always looking for new SREs. And if you have any questions, I'd be happy to answer them. Thank you.